So now for the fundamental theorem of calculus. The fundamental theorem of calculus is appropriately named because it connects two major ideas in calculus. So far we've talked about these two main ideas, the integral and the derivative. Now we talked about limits as well, but remember, we said that an integral, because it comes from that Riemann sum, is really just a fancy type of limit. So these are our two major ideas so far. And so let's do a super quick review of what the derivative and the integral mean graphically. So if I have some function, now I'm just going to draw, let's call this the same function in both graphs. So I've got the same function in both graphs. Now what my derivative does, and generally we're finding the derivative of continuous functions, so I'll actually just extend this curve. This is a hypothetical, and so let me call this y equals f of x. This is going to be my curve. Just extends in both directions. My derivative is going to give me the slope of the tangent line at any given point along this curve. So let's say I wanted to find the slope of the tangent line right here. I would have a tangent line that has about the same slope as that curve at that point. And so my slope of this tangent line would be equal to f prime of x. So that's what my derivative tells me. Now for the integral. So the integral is going to give us that area under the curve. So if I have this curve, and now this curve is going to just be over some definite region from an x of a, so let's call this x of a, to another x value that I'll call b, then the integral is going to give me this area under that curve from a to b. So the derivative, let's get this down, the derivative is going to be the slope of the tangent line at any given point along the curve. Okay, and our integral, and let's actually write out what this integral would be. This would be the integral, this would be the integral from a to b of, and if I'm calling this curve, I'll call it also y equals f of x. This would be the integral from a to b of f of x. And then we said we're going to add this dx just to show you that, that our variable inside of this curve is x. So that would give us the area under this curve. So that would give us this area right here. The integral gives us the area under a curve. Okay, now I want to be clear. In the last section too, we said that we can also find the integral when we have a curve below the x-axis and we want to find the area above that curve as well. But this is just kind of what we're going to see most of the time. So this was a generalization of the derivative and the integral. Now these are two seemingly completely unrelated ideas, and this brings us to the fundamental theorem of calculus part 1. So we've got two parts to this. Part 1 tells us that if f, so this is our function, is continuous on the closed interval from a to b, then the function g, defined by g of x, is equal to the integral from a to x of f of t dt as x goes from a to b, is continuous on the closed interval on a to b, and is differentiable on that open interval a to b. And we kind of saw these two things a lot as being required in the intermediate value theorem. And g prime of x is equal to f of x. So that's pretty much, this is kind of our big ticket item here. G prime of x is equal to f of x. So if this is true, then if I take the derivative, and let's look at this. This kind of says that if I take the derivative of g of x, so g prime of x, that this is going to be equal to, well, let me just write this notation a little bit differently. The derivative, remember we said this is okay notation, of the integral from a to x of f of t dt. And so now what this is saying is that when I take, and if I take the derivative of both sides of the equation, then what's going to happen here is the derivative is going to kind of undo the integral because they are opposite operations. And then what happens is that this t right here gets replaced by that x. So this is equal to f of x. That's what our fundamental theorem of calculus states. Basically tells us that the integral and derivative are opposite operations. And we'll talk, by the end of this activity, you'll get a better idea of what this upper and lower bound are going to do for us algebraically here. And so just a note, we abbreviate the name of this theorem, and you'll see this a lot in textbooks, FTC1, so the fundamental theorem of calculus 1, because there's more than one fundamental theorem of calculus. And we say that the derivative of the definite integral with respect to its upper limit, because this x is that upper limit, is the integrand, which is just a fancy name for what's inside of the integral, evaluated at the upper limit. So that's what we're saying with this theorem. So let's do an example of this. We want to find the derivative of the function g of x equals the integral from 0 to x of 1 plus t squared dt. Okay, I want to find this derivative. And so I know, and let me scroll up a little bit, based on my fundamental theorem of calculus, all I'm doing is I'm plugging that upper bound, which is x, in for the t in my function. So the derivative is automatically going to be what's inside of this integral evaluated at x. So the square root of 1 plus x squared. And that is literally it. That is the answer. Just a note, something that we could have seen if we had, because right now we have a lower bound of 0, right? If we had g of x is equal to, let's say, the integral from 3 to x of the square root of 1 plus t squared. So if everything else is the same, except for that lower bound, well, we would get the same exact derivative. Square root of 1 plus x squared. So it just so happens that our lower bound is 0, but it doesn't have to be, because in this theorem, the lower bound is some a, which is just a constant. So this can vary, and it won't actually affect that derivative. Okay. So this goes to show that the derivative and the integral are opposite. So derivative and integral are opposites. Well, what else did we say was the opposite of the derivative? Well, we have the antiderivative, and antiderivative, quite literally the opposite of the derivative. And so this is going to bring us to part 2 of the fundamental theorem of calculus, which is a little bit more useful. That if f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx is equal to, remember what these capital F's denote? They just show that this is the antiderivative. So this is equal to the antiderivative evaluated at b, which is the upper bound, minus the antiderivative of this function evaluated at the lower bound, where f is any antiderivative of f. And so the second part of this is such that f prime is equal to f. Well, when we take the derivative of an antiderivative, we're just left with the original function. So that's what this says. And we can abbreviate this FTC2, Fundamental Theorem of Calculus 2. So the integral, now we did a whole lot of work talking about what the integral meant graphically. We used Riemann sums to approximate the value of the integral. Now we're actually just going to be able to directly, and a lot of times pretty simply, find the value of this integral. Without any of those comparison rules, without trying to break this up into rectangles, we can just find the antiderivative of this function and evaluate that at these bounds. So let's do some examples of this. Okay. from 1 to 3, e to the power of x dx. Well, this tells me that I'm finding the antiderivative of this function. And I'm going to introduce some notation here. Well, what's the antiderivative of e to the x? Isn't that just e to the x? Well, the derivative of e to the x is e to the x, right? So this must just be e to the x. And now there are two kind of major ways that we write these things. So one, you might see this enclosed in brackets to show that we've taken this antiderivative. The integral symbol we got rid of because we took the antiderivative, and now I'm going to write this 1 and 3 on the right-hand side of those brackets. Alternate notation, so you might also see this being written as e to the x, and then sometimes we'll just put a vertical bar on the right-hand side and say this is going from 1 to 3. So this is another notation you might see. And sometimes these are enclosed in parentheses, especially if there's more than one term. And then we've still got that vertical bar on the right-hand side. So whichever you prefer. I usually tend toward brackets more. And so now all I'm doing, because this is capital F of B minus capital F of A, is I'm just plugging in 3. So I'm finding this function evaluated at 3, which is e cubed, and I'm subtracting this function evaluated at 1, which is e to the power of 1. And finally, we just want to simplify this as much as possible. Now, the only real thing we can do is we can get rid of this 1 because e to the power of 1 is just 1. And so this is going to be e cubed minus e. And that is our integral. Okay, let's do one more. And now we've got the integral from 3 to 6 of dx over x. Well, this looks a little bit strange, but we can write this differently. We can write this as the integral from 3 to 6 of, remember, just a little bit of algebra here. If I have something like, x over 2, this is the same thing as 1/2 x. We can write this either way. Well, the same goes for this dx. I can also write this integrand as 1 over x and then put the dx on the right. So both of these mean the exact same thing. And now I'm remembering the antiderivative of 1 over x, and I know that this is going to be the natural log of the absolute value of x. So I've taken that antiderivative, I've gotten rid of the integral, so I've integrated. And now I'm just going to take this from 3 to 6, meaning I'm going to plug in 6. And so I've got the natural log of the absolute value of 6 minus this function evaluated at my lower bound, which is the natural log of the absolute value of 3. Okay, now I want to simplify this as much as possible. And you remember that rule for natural logarithms with subtraction that states that if I'm subtracting 2 logarithms, I can really divide the values inside of those natural logarithms. So in other words, this is the same as the natural log of the absolute value of 6/3, of 6 divided by 3. And then, well, when I have an absolute value of a positive number, I can just remove those absolute value symbols. 6/3 is just 2, and so finally this is just equal to the natural log of 2. That is our answer. We can put parentheses around that too if we'd like. So that is what the fundamental theorem of calculus part 2 tells us that we can do.